Daniel Wacks from Newcastle, and he's going to tell us something about macroscopic vortex rings.
Thank you. First of all, I'd like to thank the organisers for giving me the opportunity to show my work. This work's been carried out in Newcastle over the last year. It's based on some experiments that took place in the 80s and 90s when bundles of concentric rings, vortex rings, were produced in experimental conditions, and well, I don't think I need to spend much time on an introduction. It seems as though that's been covered quite thoroughly. I'll look briefly at mention experiments that were conducted. I'll discuss how to model numerically these experiments. I will show how I can produce a robust translation of these coherent macroscopic vortex rings, these bundles of rings. I'll show how the instabilities develop in the rings, but nevertheless they continue to translate in a coherent manner. I'll come to some conclusions, and at the end, hopefully, there'll be time for a couple of movies. The experiments were conducted in superfluid helium-4. What we'll need, the most important point that we'll need, is to emphasize that the vorticity is singular for the superfluid vortices. So, for a single vortex ring, we have Tate's diagram here from quite a while ago, showing how the vortex ring will translate under its own self-induced velocity. This self-induced velocity is a function of the unconstrained value of the circulation which the ring can take. It scales like 1 over r, where r is the radius of the ring, and the parameter a is the radius of the core size of the ring, so related to that amount. In contrast, in a quantum vortex ring, the circulation is limited to the quantum circulation kappa, and the core size is the order of 1 angstrom. Now, in both classical and quantum vortex rings, this formula for the self-induced velocity depends on satisfying the condition that the radius of the vortex ring must be much greater than the radius of the core size. This is satisfied automatically in the quantum case, since any size which we give to the radius of the ring will be much greater than the core size of a single quantized vortex. Here's a list of the experiments that were conducted back in the 80s and 90s. There were 2 sets of piston-induced macroscopic vortex rings that were created. The first ones, conducted by Borner, used second sound and first sound to measure the circulation of the rings. Here, this is the schematic diagram from his paper in 1983. He has second sound receivers and transmitters which monitored the circulation of this vortex ring as it translated, having been produced by this piston over here on the left. Murakami in 1983 used the visualization method to track it. So he wasn't using first and second sound, he visualized it with tracer particles. In 1994, Stam produced these similar rings using the counterflow method, but he found that his rings were not as stable, didn't translate as coherently as the piston-induced ones. So the main experimental results which we would like to reproduce are, first of all, it was noted that at all temperatures that were investigated for these rings, quite a range of temperatures representing a large change in the fractional densities of the superfluid and normal fluids, that in all cases the superfluid and normal fluid circulations were measured to be the same. The explanation which was suggested in the papers was that the characteristic time to equalize the circulation and velocity fields of the normal and superfluids was less than the time it took for the rings to come out of the end of the piston. So by the time they were being measured, they were already equal circulations in equal velocities. The magnitude of the circulation was of order 1, and since the quantum of circulation is approximately 10 to the minus 3 centimeters squared per second, that indicated the presence of approximately 1,000 quantized vortex rings. These 1,000 or so vortex rings translated a distance of approximately 10 diameters of the piston. That means that in this diameter here, the ring travelled 10 diameters in this direction whilst being measured, and it held its form. It kept a constant, translating a constant velocity, and with a relatively constant circulation. So to model this numerically, we use the Biot-Savart law, full Biot-Savart law, and we follow each point of our rings. This is a typical initial condition. In this setup, there are 19 rings. They're arranged in centered hexagonal layers. That means if we look at this cross section here, this is a cut through down one of the axes, so it's showing the XZ plane, so it's a cut along the y-axis. The rings have radius r, and the core size is a. And you can see that there's one vortex which is in the center. There are 6 surrounding that, 12 surrounding that, and if we would make it larger and larger, there would be more and more in each layer. What's important to notice is that the intervortex spacing, which is in the initial configuration, is a function of the choice of the core size of this macroscopic ring. Now, in the experiments, of course, as I mentioned, they were conducted at finite temperature, and being at finite temperature, there was a normal fluid fraction, and that gave rise to the measurements of the circulation of the normal fluid. Now, to make things simple, we'll put in an imposed normal fluid velocity field, so we don't need to model the whole, evolve the whole of the Navier-Stokes equation, coupled to the superfluid equations. And this is going to prove very useful because the rate at which the radius of these rings will shrink is a function of the difference of the relative velocity, the difference between the normal fluid velocity and the superfluid self-induced velocity of these rings. In other words, by adding a normal fluid, we'll cut down on the rate at which these rings will shrink. With no normal fluid, with no normal fluid macroscopic ring, the rings would shrink very quickly. I hope to show a movie at the end of what happens in that case. But by adding a normal fluid macroscopic ring, this will, to a large extent, cancel out the effects of the mutual friction in killing the rings. The way this normal fluid ring is built is by noticing, in this picture on the left, I have shown how a single vortex on the outer shell of the macroscopic ring travels around, how one on the middle shell travels, and how the center one doesn't move very much at all. It looks from this that the inside the core of the macroscopic ring velocity scales approximately like r. You see that the outer one moves approximately the same number of degrees around, but a much further distance. And outside that core, the velocity scales like 1 over r, which is the same as the velocity field around a single quantized vortex. So we construct a normal fluid, imposed normal fluid velocity field, which looks like this. That inside either core A or core B, we have a contribution which scales like r, and the contribution from the other core, which scales like 1 over r, and outside that, both contributions scale at 1 over r. So we have, in other words, we have a heavily weighted contribution within the core of the macroscopic rings, which hopefully will, to a large extent, nullify the effect of the mutual friction in killing the rings. So these are snapshots of the results. So we're evolving, again, according to the Biot-Savart law. We start off on the left-hand column here at time equals to 0, with 19 rings in each case. The top row is at 0 temperature, so there's no normal fluid. The middle row is at finite temperature, but without a normal fluid ring to nullify the effects of the mutual friction. And the bottom row is with a normal fluid ring. And we can see that at 0 temperature, the ring translates nicely. These are at 3 consecutive times, 1, 2, and 3. In the middle case, where there's at finite temperature, the ring starts to fall apart. And when we put back in a normal fluid ring, the ring holds together again. The distance traveled by the ring is we can measure in number of diameters which the ring travels. So, for example, in this case, we have the 3 cases. In this slide, we have the 3 cases I mentioned. We have in red at 0 temperature, so that the red line shows how the ring travels at 0 temperature, and it succeeds in reaching 10 diameters. That's over here. At finite temperature, with no normal fluid ring, the ring dies very quickly. You see how it picks up speed at the end as the ring shrinks very rapidly. And at finite temperature, with a normal fluid ring, that's the blue line, it travels very nicely, translates very nicely, also reaching 10 diameters. At 0 temperature, the reconnections occur after the ring has travelled a certain distance, mentioned here. After it's travelled 4 diameters, the first reconnection occurs. These reconnections build up, and there are Kelvin waves which develop along the lines. There's a side view and a rear view of the ring after 40 seconds. It still has the overall shape of a ring, but there are only 3 out of 19 rings left. The other rings have reconnected and joined together. And in this plot, you can see the red dots are the fraction of the line length, which is in line with the direction that the ring is moving. So it grows as time progresses until eventually there wouldn't be much difference between the fraction of line length in any direction as the ring becomes more and more turbulent. Whereas at 0 temperature, the ring, notice this is at 40 seconds. At twice that time, 80 seconds, the ring is still very smooth at finite temperature. This is because the mutual friction damps out any small scale perturbations which occur, and the fraction of line length which develops in the direction of motion is much smaller than in the 0 temperature case, and it seems to have steadied out here. So to give my conclusions, then hopefully it will be time for 1 movie, 2 movies. You'll let me know. I've evolved systems of up to 19 vortex rings using the full Biot-Savart law, with and without an imposed normal fluid velocity field. Both cases translate nicely for at least 10 diameters. They remain coherent. They have reasonably steady translation velocities. And I'd like to show 1 movie of how we see, in this case, we saw before leapfrogging of 2 rings. I'd like to show a generalized leapfrogging which occurs in a case of 7 rings. You'll see in this case that the orange ring remains in the middle. That's the central ring. The others come in the middle and go around outside the top.
Okay, any questions? Have you compared this with experiments?
That's what I started off with. There were three experiments.
Right, but now you have results, numerical results. Are you comparing the
Yes, very much so. The experiments produced rings which translated 10 diameters. I've also produced rings which translate 10 diameters.
Andre.
Well, about here, the limit of zero temperatures. Yes, some amount of energy goes into this random Kelvin wave component. I understand it's a small fraction of the total energy. So what happens to the energy balance? Does the average radius of the ring shrink?
At zero temperature?
Yes, after you allow the reconnections, unleash those reconnections.
Because I can only report that up to the reconnections, the temperature is conserved. That was mentioned on one of the slides. After that, the temperature goes crazy. It depends on the reconnection algorithm that's used.
Why don't you can keep it zero, you know.
So
It's simulation. Why the temperature? I mean, your computer is getting that photo.
Could you try to have a ring with a twist?
you mean to build in a twist into the ring in the initial condition?
Yeah.
Yes, so that is something that has been looked at, but I didn't have time to look at that. But it's a good idea.
It survives?
So with a twist, yes, it also survives and also translates. It has effect on the translational velocity, though.
They don't run.
Okay, our next speaker